Welcome back, students. In this lecture, we will start learning what is surface integral. And before surface integral, which is a very important part of the vector integration or vector calculus, we will revise our knowledge of writing a line vector, and with the analogy of that we will write the small surface vector, and then we will learn surface integral in the progressive way. So let us start. Just for the sake of revision, let us consider a 2D plane. Let this be x-axis and y-axis, and the origin is marked as O, and this is some vector v which has magnitude v. So you know that projection of the magnitude v on x-axis is this line segment that I have marked on x-axis, and let us say this OA, and the projection of this magnitude v means length of vector v on y-axis is the segment I have marked by OB this. So you already know that I is the unit tangent vector on along x-axis and j is unit tangent vector along y-axis. So you can write V as OA I plus OB j means just what I want to remind you that a vector can be written as a vector combination or vector sum of its component vectors, and components are just obtained by the projection, and the same analogy will be applied to find a vector surface. So suppose we have a surface, very small surface, for the sake of starting we have a very small surface and its projection, and you can imagine that if you have a surface and have a torch which can generate parallel beam, so you put it focus of torch on that surface, the image will be reflected on some plane. So the image is just the projection. So if you have very small surface, you can take its projection on all the three planes, and those projections will form the component vectors, and the sum of component vectors will be surface vector. As we have seen, sum of component vectors OAI and OBJ is the vector V. So let us draw a 3D system. Let this be x-axis, this be y-axis, and this be z-axis. And suppose we have some randomly oriented surface S in XYZ system, XYZ Cartesian coordinate, and let us take very small surface area, and that we denote by ds. We will consider this in separate steps. So as a step, first we will see what is the ds vector. So number one, let us mark this small surface area in large from, suppose you are viewing it with some microscope, and let this be uh, unit vector e1, this be unit vector e2, and lengths of these are this. Lengths be let lengths be denoted by L1 and L2. So unit vectors are E1 E2 and lengths are L1 L2. I am writing more clearly so that you can see it. So this has length L1, this has length L2, and this has unit vector E1, this has unit vector E2. So what is this surface area? And the surface area is actually ds. So what is ds? You know ds can be calculated as magnitude of cross product E1 L1 E2 L2, and because L1 L2 are lengths, these are positive, so this is simply L1 L2 E1 cross E2, and E1 cross E2 is a vector which is normal to both E1 and E2, but E1 E2 are unit vectors, so this means this is equal to L1 L2 and a unit vector perpendicular to both E1 and E2. The unit vector perpendicular to E1 and E2 will be also perpendicular to the surface, means this is outward drawn surface normal. This will be something like this n. So we have ds given by this, so ds vector is obviously L1 L2 unit vector n. This is the vector for a small surface area. Now we will learn how to represent this vector as a combination of projection vectors. So again, suppose you are taking images of this surface ds on xy plane. So on xy plane, suppose this is the image and it has with dimensions dy and dx. So what are the area of this? So area of projection of ds on xy plane. What is this? Area of projection of ds on xy plane. What is this? This is simply dx dy, or you can also obtain this from the vector. So this will be magnitude of dxi cross dy j, and you know that this is dx dy I cross j, and that means dx dy I cross j is k unit vector. So this is just k, and this means this area, and suppose we denote this area by ds xy, means projection on xy plane. So ds xy is dx dy k, this magnitude, and therefore the vectorial form can be denoted as dxy is equal to dx dy k. Similarly, the projection on yz plane, and let me denote it by dxyz. So this will be dy dz I, and the projection on xz plane, and let us denote it by ds xz. So this will be dx dz j. Now you know that vector can be written as a combination of its projection vector, means component vector. So we can now write the ds vector as dx dy k plus dx dz j plus dy dz I, or in a systematic manner you can write ds vector as ds ds vector as I dy dz plus j dx dz plus k dx dy. So this is how we denote a surface vector, and now we will learn how to write the projection vectors in form of angle, means simple scalar function. So you already know the projection of ds on xy plane. Projection of ds on xy plane is dx dy, and it means ds cos theta is equal to dx dy, but cos theta is what? Cos theta is just n dot k. So ds n dot k. Why n dot k? You already know that angle between two surfaces is found by the angle between their normals. So normal, unit normal to ds is unit n cap, and unit normal to xy plane, means dx dy, is k cap. So n cap dot k cap is cos theta. So this is equal to dx dy, and when needed we write ds as dx dy by n dot k. And similarly, sometimes when needed, we write ds as dx dz by n dot j, and ds is equal to dy dz by n dot I. So just remember these formula when we integrate or when we perform surface integral in vector calculus. We many times need to simplify the integral, and direct integration is sometimes very tough. Most of the time it is very tough. Then we use this simplification, means we take the projection on some plane and write ds is equal to one of these forms. So let us see when we will use which form. Suppose suppose v be a vector function defined or acting on a surface S, given by phi x y z is equal to c, means this surface S is given by phi x y z is equal to c. Now the integral of v on S is given by, and integral of v on S is called surface integral of v, because S is surface. So this is given as double integral over the entire surface S, and v dot ds, and you already know what is ds. So ds is a small vector, and also ds is equal to n ds means unit vector n and the magnitude ds. So this can be written as double integral or surface vector n v dot nds, this v dot nds. So you just need to find v dot n and then integrate with respect to s. So integration with respect to s is not always easy, so we will take its projection. So we will write it as this surface v dot n and dx dy by n dot k are, this is equal to v dot n and dx dz by n dot j are that this v dot n and dy dz by n dot k. So we will integrate by using one of the three forms. The only thing that remains here is what, how do you find n? So you already know how to find unit normal on a given surface, because surface is denoted by phi xyz. So unit normal n is gradient of phi, and that divided by magnitude of gradient phi. So in simple steps, when you have to integrate a vector v on a given surface S, first find the unit normal to the surface. And that is grade phi by magnitude of grade phi. Second, calculate vector dot n, and third, write one of these forms and integrate. Just after writing in this form, we will need the limit according to the variables used. For example, if we use this form, we will need the limit of y and z, and the shape means projected shape will be lie on yz plane. So this is the summary of how do we integrate surface integrals. Sometimes it also may be case that you are instructed to integrate a surface integral, means find a surface integral without using the projection, then you can directly integrate. As suppose this be 3D system x, z and y, and we have a surface S and a vector v acting on S throughout. Then to integrate, so let v has the form v1 plus v2 plus v3 and we have just few minutes earlier discussed that ds is given by dy dz I plus dx dz j plus dx dy k. So you need to find out integral for the entire surface v dot ds, and that comes out to be the integrals v1 dy dz plus integral v2 dx dz plus integrals v3 dx dy. And now the limit that we will require to put in these integrals will not be taken from S, but the limits will be taken from the images of ns on these different planes. So this is sx, this is sy, sxy, you can say this xyz, this is s xz, and this is s xy. Sxy, this is just symbol, and that means you have to take limit of the component of this surface in xy plane and limit of component of the surface from xz plane, limits from the component of surface in yz plane. So now we will take an example and solve it using both the method direct and projection so that you can understand it deeply. So now let us start our first problem and integrate integrate the vector v is equal to the vector v is given y z I y z I plus x z j x z j plus x y k on the surface of a sphere x square plus y square plus z square is equal to a square in first octant. And you already know what does first octant mean. So very first thing that we should find the unit normal to the surface, as we have already discussed. So let phi is equal to x square plus y square plus z square is equal to a square be the surface, be the sphere. Surface means surface of the sphere. Then n is equal to, or simply just first find the gradient of phi. So del phi you have already obtained del phi for this, so this is 2 times xi plus yj plus zk. And what is unit normal? So unit normal is just del phi by magnitude of del phi. So this is 2 times xi plus yj plus zk and square root of 2 times x square plus y square plus z square. 2 cancels 2 and x square plus y square plus z square is equal to a square. So we have 1 by a xi plus yj plus zk. This is our unit normal, and as we have already discussed, we will find v dot n. So v dot n becomes yz yzx plus xzy plus xyz, and 1 by a is a part of unit normal, so this becomes 3 by a xyz. So we have obtained n. What is the surface integral now? Surface integral this is equal to this surface integral over this surface S, and v dot n ds. We have just summarized this, so just write these values. So we get this surface integral is equal to integral over the surface S 3 by a xyz xyz ds xyz ds. And as we have already discussed, take the projection of ds on xy plane. So you can see that if this is the sphere, its image on the xy plane will be just a quarter circle. What you can see here, this x square plus y square is equal to a square. This will be image on xy plane of the sphere in first octant. So this circle means this quarter disk, this will be image. So you can also write this as this, and now region will be changed, region will be taken as this one. So this 3 by a xyz, and ds become dx dy by n dot k. And we have already discussed this, that we will write ds is equal to dx dy by n dot k. We have discussed multiple times. So we have already obtained n, and we know k. So what is n dot k? N dot k is n dot k. You can go back to the video and see that n dot k becomes z by a. So write this value of n dot k here, and we get this over the region on xy plane, this 3 by a xyz dx dy divided by z by a. So you can see that z by a will cancel z by a, and we have just double integral over the region. 3 by 3 can be taken outside. This is just xy dx dy, and mark that I have written s in the previous integral and r in this integral. As where we have taken ds means we are integrating over the surface of the sphere, and now we have taken projection on xy plane. So now spherical surface is not in our integral. We are integrating over the surface of projection. And what is projection surface? This is the circle I have already drawn. So the limits that we will use will be from this circle, means x square plus y square is equal to a square. This circle will give the limit for this. So you already know how to integrate this. Let us integrate finally. So this surface integral I, this is 3 times double integral xy dx dy, and put the limit. This is x square plus y square is equal to a square. This is x-axis, this is y-axis. So it is also easier to convert the variables into polar coordinates. So let x is equal to r cos theta, and y is equal to r sin theta, so that r will vary from 0 to a because a is radius, and theta will vary from 0 to pi by 2. You can see in the figure. So 0 to pi by 2. We have already discussed the same thing also, how theta varies. So this is 3 times, and 0 to pi by 2 for theta, and 0 to a for r, and xy means r square sin theta cos theta, and dx dy is r dr d theta. We already learned this in the Jacobian system. So this is 0 to pi by 2 and 3a is 3 sorry, this is not a, this is 3 and r cube sine 2 theta by 2 dr t theta. So because these are 0 to 8, these are constant limits, so you can integrate separately. So 3 times r integrates to r to the power by 4 and the limit is 0 to a, and sine 2 theta by 2, this integrate to minus 1 by 4 cos 2 theta, and the limits are 0 to pi by 2. So you can find this as this 3 times this is a to the power 4 by 4, and this minus 1 by 4, and at upper limit cos theta is equal to pi by 2, so cos 2 pi by 2 means cos pi means minus 1, and at the lower limit cos 0 is equal to 1, so this will become 2. Just put the limit and you will get this. So this is now 3 by 8 a to the power 4, and we will now integrate the same vector with same on same surface with the direct measure, so that you can understand what is being done during the integral. So let us do the same thing direct way. So what was b? B was yzk y z I plus zx j plus xy k, and what was ds? Ds we have already discussed. This is dy dz I plus dx dzj plus dx dy k. Now we take v dot ds, so we get yz dy dz plus zx dx dz plus xy dx dy. Now this surface integral was defined what? Surface integral was defined as v dot ds, means we obtain these integrals yz dy dz plus integral zx dx dz plus integral xy dx dy, and the region of integration is same by now. But now feel that we have this surface integral and we want to put the limits. So we actually we don't feel, just we have these integrals and we want to put the limit. So let us name these, I mean don't feel, just realize. So let us name these integrals as I1 plus I2 plus I3. So we will consider one by one. So what is I3 now? I3 is, we start by taking an x, y, dx, dy integral. So I3 is this double integral and x, y, dx, dy, means we need the limits of x and y. So how do you find this? So let us describe this on the figure. I3, because actually it is I have cited it very times, it is very tough to visualize in the 3D plane. So this and this is the form of a sphere that looks like. So because the I3 does not has, I3 is x, y, dx, dy, so it does not involve z, means we need to find the limits on the xy plane. So we have already discussed that on xy plane there is just a circle, x square plus y square is equal to a square. This is a comma 0, this is 0 comma a, this is x axis, this is y axis. So means this whole region is considered while taking I3. So just put the limit. So limit 0 to a, this is for x, and 0 to square root of a square minus x square, this is limit of y. We have already learned how to put these limits. So you can integrate this. This is simply 0 to a, and we will integrate y first. So this is 1 by 2 y square 0 to square root of a square minus x square dx, and this is 1 by 2 0 to a x, and then y will take the limits a square minus x square, so it becomes a square minus x square dx. And I hope you can integrate this very easily, and you will get 1 by uh, 1 by 8 a to the power 4. Similarly, when you integrate I2, you will get 1 by 8 a to the power 4, and when you evaluate I1, you will also get 1 by 8 a to the power 4. So because surface integral is I1 plus I2 plus I3, we again get 3 by 8 a to the power 4. So this is how did integration, how do we integrate directly, and we have also integrated using projection rule. So you can see that integration with the projection is comparatively much easier than the direct integration, because in this process you have to integrate in each plane, and if you take projection you have to integrate only on one plane. So finally, I hope you have understood what is the concept of line integral and what are their applications. And in next lecture, we will continue vector integration, but we will discuss this surface integral in the context of vectorial surface. So keep waiting for the next lecture, and till then, keep on your study for previous lectures and this line integral.